Alright, in this review session, we are going to look at communications and op-amps. You would generally expect one question each. Very rare you don't get anything lah. So chapter 16, you will get one question. I think generally anywhere between 6 marks to 10 marks. Don't know, you don't know one. And chapter 21, another one question. Anywhere between, again, 6 marks to 10 marks. Okay, it's a confirmed question. So the good thing about this confirmed question is, you know you study, it will come out. So if let's say you were here last afternoon for the medical physics one, you will notice that maybe you study very hard for this CT scan, but it didn't come out. Maybe you study very hard for this MRI, but it didn't come out. Or you study really hard for ultrasound, but it did not come out. X-ray came out instead. So it's a bit not worth it. But this one you can confirm guarantee got one question. So I think it's okay, especially if you're like the last minute study and you want to get in as much points as you can. So we're going to start off with chapter 16 first, okay, which is communication. There are a few ideas around communication that I think in a summary format, the best way to recall the main ideas is that block diagram of ADC and DAC. And then I will zoom in part by part to do a question each. So let me find that block diagram first. Chapter 16. Ding, ding, ding. So the so-called block diagram is this one. Wow, small. Okay. So when it comes to communication, right, the whole idea of communications is how do we use circuits to transfer information from one point, excuse me, from one point, so here all the way to here is the transmitter. I'm talking to the mic. The mic is the transmitter now. So everything in my room is the transmitter. And then here to here is the carrier. So we will call this the communication channels. There are many options here, but most of us are using Unify. Or maybe if you are using your phone to watch this, then you probably are using your mobile data. So that could be a satellite, could be an optic fiber communication channel. And then everything here is the receiver. So on your end, right now, you are hearing my voice, hopefully clearly, through a speaker. Either a small, tiny speaker in your headset or your speakers in your PC. And this is the mic. So we are trying to transfer energy from one point to another point. And every step of the way, there are questions that they can ask. So the first one, we are going to talk at what happens at the transmitter. So the first type of question, which is more popular. So there are two types of questions that are more popular and then one type that's not as popular. The first time that is popular is this ADC. Okay, because I don't know about you, but there's no spirit of Miss Lee that go into the computer and then travel all the way to your computer and whisper physics in your ear, okay? It's no, it's just electrical signal. So the first thing we're going to look at is the ADC and the DAC transmission. So that's the first type of question, ADC. So this is the analog to digital transmission, or conversion actually. So when it comes to analog to digital conversion, you have to know the definition or basically the function of an ADC. Okay, so in this converter, we are taking analog voltage sample at regular intervals, okay, and converting it to binary numbers. So in a nutshell, what we're doing is we are taking, let's say this is my noise, my sound, my voice. We are sampling it at regular frequency. Okay, so once we sample at every single line, what we do is convert what we sampled to ones and zeros. So to convert this one to ones and zeros, what the circuit will do is will cut here, cut here, cut here, cut here. So you get this kind of like diagram that looks like this. I don't know if you remember or not. Like this one, like this. All these kind of ones and zeros. And then convert this to 1 1 0 0 0 1 1 0 1. Okay. So here there are already some past year questions which are pretty popular. So I would probably give this a 3 star. Meaning if you intend to spend some time in communication land, you should be able to know how to do analog to digital conversion like this. Okay, things that you need to know beyond just how to convert is also the name of the blockchain and the role of every single device. So for example, the parallel to serial converter is to take simultaneous bits of binary numbers and then transmit them one by one. Okay. So we will know what is the purpose of every single equipment here and here. All right. So this is the first part you need to know about the transmitter. We are changing analog signal, which is the actual sound wave, to digital signal, which is the ones and zeros. All right. So we'll do a question now to show this part of the conversion, and then we will then move on to the second type of question. So let me go and take a question from past year. So there's a question like this in Variant 4.2, I believe, for ON20. Yes. So we'll try an example now. ON20, paper 4.2, question 4. Crop the screen. Okay, familiar stuff. You stare at this first. Oh wait, I can't. I need the big screen. I need the big screen. Clear graph. Ding. Okay, so we get this weird sounding wave. They can give you any shape that they want. You don't have to panic. And then they will tell you some information about the sampling process. Okay, so we will examine this recollection of all the other information about sampling that you need to know if you haven't watched the video yet. Table, a lot of information. Give me a sec. So if a question like this comes out, right, it's pretty good because it's at least 8 to 10 marks, okay? And if you know how to do it, it's a pretty easy mark to score. That's the entire paper for, right? If you know, then easy lor. You don't know, then GG lor. Okay, so hopefully you have found the question in wherever you look at past year questions. All right, so this thing is 3 marks. So I'm gonna put down the marks for us. 3 marks. And the total is 9. 9. Okay, let's do the question. So first thing, state the advantages of digital data rather than analog form. So in the video, I compare in detail, or you can refer to your notes, compare in detail why we prefer digital compared to analog. But the main reason is still because digital is safer lah. And also for digital, we can, what's that word? Encryption for better security. Okay, so the two advantages, I'll give you three lah. All right. So the first one is the digital signal. So whenever someone sends you a WhatsApp message, they will say there's end-to-end encryption, meaning hackers cannot read your WhatsApp message law. All right. So can be encrypted for better security. All right. And then you can say, second point, signal can be regenerated. Okay. And noise can be removed. Sometimes they can ask you what is noise. You could also say that digital signals are actually it's not the digital signal, it's the the circuits more reliable and cheaper. But the mark scheme underlines circuit, so circuits must be there lah. So 3 should be more than enough for you to answer. But I think this one is the main reason. Okay, so we can encrypt the signal and the sound can be signal can be regenerated, your noise can be removed. Okay, so the reason why we don't use analog is because analog will pick up noise. So regenerated helps with attenuation or helps overcome attenuation. Hopefully you know what attenuation is. Attenuation is the power loss or loss in wave power as the signal travels in the medium. Don't forget your signal is still electromagnetic radiation, which is a wave. Travels in a medium. Okay, and then noise can be removed. This noise is known as the unwanted signal that is superimposed on information signal. So for example, my voice now is the information signal that you want. The unwanted noise, unwanted signal is maybe the thunder, the lightning, my neighbor's chicken. Sometimes it will crow in the middle of the day. I don't know why. Or my alarm. Okay. So yeah, circuits are more reliable and then they're cheaper. So an analog signal is to be transmitted in a digital format. So we're going to do the analog to digital conversion. And this is the analog signal, the input. So normally this kind of mic, there's a piezoelectric crystal or piezoelectric transducer. And the piezoelectric transducer will convert these signals, will convert the vibration of my voice into electric signal. We also talked about this yesterday, right? For your ultrasound. So right now, me talking vibrates the crystal inside my mic, and the mic will send this kind of output voltage into the circuit that is my computer, right? So now, so now we're going to continue. This analog signal is sampled at the interval of 0.10 millisecond. That means I sample one time here, sample one time here. Every 2 big boxes, I sample once. Some value of the analog signal and the corresponding digital signal is shown in the table. Each digitized number contains 4 bits. Okay, so this is the analog signal. So now we're going to do some data collection. At different time, we will get different signal. So for example, when t is equal to 0, the signal is 0. When t is 0.1, the signal is 5.7. Is it 5.7? Yes. So this one is 5.7. 0.2, this one is 6.2. And this one here is 3, right? 1, 2, 3, 4, 5, yep. 0.4, this looks like 4.8. And 0.5, this looks like 1.0. So I will copy in all these numbers, 6.2, 3.0, 4.8, 1.0. So 6.2, 3.0, 4.8, 1.0. Yay! In table 4.1, underline the LSB, least significant bit, in the digital signal for the time of 0.2 millisecond. You don't go and make a mistake and go and underline for the first timing, okay? 0.2 millisecond, this is 0.2 millisecond. So take the time frame, follow the question now. Read the question slowly and follow it. Okay, so the least significant bit is the last bit. This is your LSB. Because this doesn't give us, this one is the smallest data reading. Whereas the most significant bit is the first one. In case they ask for most significant bit, this is your MSB. But in this question, there only one LSB, okay? Don't go itchy hand and draw both. This is what we want, 1 mark. So you underline this 0, you will get 1 mark. Just underline one time, can now. One time. This is your LSB. Okay, next part. Complete table 4.1. Okay, I've written the digital and binary number. So now I have to convert to ones and zeros, depending on your method. So some people will memorize, some people will have a conversion that they can do at the back of the paper. I am just going to use my calculator for this, okay? So I will tell the calculator that 3 is decimal, and then I will convert to binary, which is 0011. Repeat again. Decimal. Okay, so now 4.8 is decimal. We cannot take 4.8, we will take 5. Okay, so this is because we always round to the lowest integer. If you haven't passed the threshold to 5, that means you are not yet 5. So this one will be 4. Does that make sense? So let's say your circuit is like this one. This is 1, this is 2, this is 3, this is 4, this is 5. 4.8 is here. You reach 5 already, not yet. So the circuit will give the reading of 4. So this one will be a binary number of 4. It's a bit like you need 4.8, but you need 5.0 to get an A. So is 4.8 a 0, a A or a B? 4.8 is a B. Does that make sense? You need to reach the threshold, then only we can move on to the next integer. Okay, 80 mark is A. 79 is B. But me 79 round already become 80, I know, but still B. Okay, haven't reached 80 yet, still B. Make sense? So you haven't reached 5 yet, you are still 4. So this is 4. We're going to convert decimal. So 4 is decimal. Then we convert to binary. 0, 1, 0, 0. 0, 1, 0, 0. Okay. And 1 is 0, 0, 0, 1 lah. No need to press lah, this one. Okay. So you have all the binary number correct. You will get 1 mark. So everything here correct is 1 mark. Everything, this one and this one correct is 1 mark. And finally, this one, if you read 4, you get 1 mark. If you read 5, you don't get this mark. Okay. So now we have all these ones and zeros. And it says that a single bit from the output of the digital to analog converts to an output of 1.0 millivolt. Sure, assume that the conversion and transmission, there's no time delay, no lag. On the axis, show how the output digital to analog converter will look like. 3 marks. Okay, so here, let me go back to the blockchain. So all this happened in the transmitter. We have convert things from this shape to a bunch of ones and zeros, and then we send it to the parallel to serial converter, and then now we are ready to transmit. So let's say we transmit along the communication channel, and then now it has received the ones and zeros. We want to rebuild the signal. Hence, digital to analog converter. We want to rebuild the signal, and the signal that we rebuild will look something like a series of steps. Hopefully will look like this one, but no guarantees. Okay, so now we're going to build back the steps, but if you want to build back the steps, it's actually pretty straightforward. Instead of worrying too much, you're already converted to the analog signal, right? So the analog signal from the perspective of this digital signal, when we receive the digital signal, let me crop the digital signal first. This is the digital signal that we receive from the transmitter perspective. Okay, I know this is 4.8, I know this is 5.6, sorry, 5.7, 6.2. The 0.7, 0.2, 0.8 is missing in translation. We cannot get it back anymore. So sometimes when you watch recording, either I speak too loud or something happened and then my voice get clipped, the signal is missing. So right now what we have is this one, and we need to convert it back to analog. So the analog signal, this is 0. Remember how this one used to be, so this will be 0, this will be 6. No, sorry, no, this will be 0, this will be 5. And this is 6. So 0, 5, 6. Okay. And then this one, 3, 4, 1. So this is 3, this is 4, this is 1. Of course, you can convert everything again, but why should you anyway? And as a sign that we haven't reached 5, this one is 4.8 become 4. You see this 5.7, 5.7 become 5. You can always double check one if they give you answer. Like for example, this one is 0, 1, 0, 1. This is binary. If we convert to decimal, this is 5. So this one also we took 5, not 6. Sorry, and then this one we take 6. This one will take 3, 4, 1. Okay, so 6, 5, 6, 3, 4, 1. Time to draw. Okay, so at time equal to 0, our reading is 0. So it will be 0 all the way until the next sampling. We sample again at 0.1 millisecond, we will get 5. 5, 5, 5, 5, 5. Until we sample again, we will get 6. Sample again, we get 3. 3 is here. And finally, sample again, we will get 4. 4 is here. Miss, cannot draw 1. No, cannot draw, no space. So this is the graph. Maybe a bit cannot see. Hang on, let me change color. This is the graph. Can see. Okay, this one. Compromise. So you draw like this, you get 3 marks already. Very nice, right? Okay, do you need to join the steps? Not really, but since all the textbook join, I also join now. Like this. This is 3 marks, Mian. Okay, so if you draw a bunch of steps with the right width is 1 mark. I'll show you the mark scheme now. So it's pretty good, this one. It's like you don't really need to do much beyond just convert the data. Okay, the girl can see now. Okay. So a series of steps, all of width 0.1 millisecond. The step level in order of input is 0, 5, 6, 3, 4. 0, 5, 6, 3, 4. Okay, all levels is correct, you get 2 marks. One of the level not correct, or one of the level missing, or for no unknown reason, you can show 1 millivolt. There should be no 1 millivolt in your graph. Then you will get 1 mark. Okay, so this question is pretty okay, this kind of question. So if it comes out, that's great. Okay, a few things that you should know about this beyond the advantages of digital transmission to answer question like this is sometimes they will ask you how to improve the signal quality, because I don't know about you, but this looks nothing like this. I put side by side and then we laugh at it, okay? This looks nothing like the original signal. I mean, I can see a bit, like you see this dip is for this one maybe. This rise is maybe for this one, but dude, come on. It doesn't look the same at all. Hamilton will sound like robot. Okay, so what can we do to make this signal, blue color one, looks more like the original one? So to improve signal quality, we can do two things. We can increase the sample sum to improve signal quality. Two things. One, we can increase sampling frequency. So in the video that we recorded, we got show many examples. We let you listen to music and determine the sampling frequency. But right now, no time lah. So sampling frequency means if I sample at 0.05, I may be able to register this maximum because this maximum is totally missing. Okay, so this one will decrease the step width. So instead of having a 2 cm step width, we will have 1 cm step width. The smaller the step width, the better. Let me make this bigger. Okay. And the second point is to increase the number of bits. Right now, you only have 0 to 7. 4 bit is only 0 to 15. Okay, so we want this because we can decrease step. Okay, so yep. English issue here that I wish to point out. Step width is also known as depth. So this width and depth is here. D. Okay, the height is here to here. H. So if we keep decreasing, right, then hopefully, wait, let me show you a picture. Hopefully with enough changes, this will happen. Yeah. So this one is not very nice because the red color shape is the shape that we want. You increase the step, increase the number of bits. Is it increase the number of bits? No. If you increase the sampling frequency from 5 Hertz to 10 Hertz, you can see the depth. This is the depth or the width decrease. So from here to here to here. Wow, look at this. The depth is small, so we have closer to the original graph. We could also increase the bit rate. Like for example, this bit rate is only 2 bit. So you see the step height, wow, so tall. Looks nothing like the graph. This one will look more like the graph because I increased the number of steps. So each step is smaller. And then this one is the best one. It's just that you got more data to transmit lah. More lag. Okay. So this one is to improve signal quality. If you know how to do all of this, you can answer this question with almost full mark. You just need to go and practice to do some. Okay. So I'm going to provide some suggested question for you to do or to try. Pretty sure some is already recorded, but let me go and dig a bit. Okay, so this tool is already recorded. You can watch and learn. And if you want more questions to try, that would be here. I think if you do this much, you are okay already lah. Yeah. Okay, just 5 questions. You gotta practice a bit. So this tool is recorded. go try some lah. Do at least 3 out of these 5. Then you are good. All right, so this is the first type of question. So we have settled this part at the transmitter. We have settled this part at the receiver. Next part, we need to talk about the communication channel. So the communication channel in between here includes attenuation. Why? Because right now, I don't know where you stay, but if let's say you stay very far away from my house, because I stay in Kepong, or even further, Miss Ellie stay very, very far away. To sit, have to go highway 1. So you can still attend class because we have this beautiful thing called the internet. So attenuation will happen, and sometimes we need to regenerate the signal. So when it comes to communication channels and attenuation, the questions will come together most of the time. All right. So this is the first type of question. Go try some. The second type of idea would be communication channel, or what I like to call the cable subtopic plus attenuation. 2 things you need to know. Number 1 is what are the types of communication channels. So in your notes, as usual, I have provided very detailed breakdown. But in case this is the night before the exam and ain't nobody got time for that, let me try to see if I can find a more abbreviated summary. But because it's abbreviated, sometimes you don't have enough information. But you know, sometimes you just want to pass. Okay, let me see if there's a summary somewhere. Nope. Textbook also give list. Sad. Okay lah, I'll type the summary for you. Okay. So let's draw a table. So there's different types, and there is the advantages, and then there's the disadvantages. Let's put 16 and put big. Okay. The first one is wire pair. Example, your headphones, your 3.5 mm jacks, the headphone. Hang on, let me see if I can increase everybody's size. This is too small, bro. Okay, so 3.5 mm jacks. Okay, the advantages here is that it is cheap. Okay, the disadvantage here is short range. Right, short range, and then low security, can be easily tapped. So old phones uses the wire pair lah. Older phone networks. So sometimes when I was a kid, I like to play with the phone at home because I got nothing to do. And then what do kids do anyway? So I will put up the phone, and sometimes I can hear other people talking in the phone. Like I eavesdrop and I feel very accomplished because I'm listening to a conversation that I'm not supposed to listen to. But now it's not possible anymore lah, okay? So the second one is coaxial cables. This is like TV cables. Not HDMI, but the TV cables. Okay. This one, you need to know the actual setup. Basically, you need to label the cable lah, okay? So I'm not going to label. I'll just show you how it looks. So this TV cable, it has this the main character here. The reason why it is so special is because you know the problem with low security and short range, and then can pick up noise easily. We can settle all this problem by this wire braid that is providing shielding. Sometimes they will ask you to memorize or label the signal. So this short range, low security. What did I do? I don't know. And it can pick up noise easily. So for our coaxial cables, the main idea here is that the wire braid is a plus. So our wire braid, okay, shields the conductor from noise and interference. It protects the signal. Very nice. All right, next. Disadvantages. So because of this, by the way, there is less crosstalk. Okay, there is this one. There is crosstalk. So here, this one is less crosstalk, and also can travel distance, longer distance, longer range. Okay, and use digital signal. Disadvantages are money lor. This cable need more money to make. Expensive. And the cable is thick. Okay, that's all. Range is not the best, but it's good enough. The next one is optic fiber. Okay, so optic fiber is your Wi-Fi, not Wi-Fi, sorry, your Unify is optic fiber. Okay, I think Maxis now is also bringing up optic fiber. Okay, so this one, the main point here is that we can send large amount of data. Light can carry more data. Travel large distance. Okay, not affected by power surges because it's light. This is still electric signal. Suddenly got lightning very large at the side, it will affect the signal one. This one not so much. Okay, so harder to tap. So as you can see, the cable is improving, but as we improve, more expensive. Okay, and then 2 cables needed for communication. So if you install Unify in your house, if you change from your broadband to Unify in your house, right, you will notice that the person have to come and drill a hole in your wall one to install a second cable. Okay, this is the reason why. But this is very fast. Speed of light. High frequency speed of light. Yeah. All right, next. Satellite dish. Light link. So when it comes to the satellite link, right, or your parabolic dish, we like this because this is wireless. That's the main point. Okay, so I'm just going to crop the notes now, right? This one, they seldom ask one. We use radio wave for this. So this one, we are using light. Actually, it's close to laser, the length. Okay, never mind. I need to go and Google the actual length. It doesn't matter. Okay, so the satellite link or your parabolic dish, okay, means we will choose aerial, different types of aerial, okay, so that we can decide whether we want to take all the radio wave or just radio wave from one direction only. So your astro dish is a satellite link. The astro dish on your house, the roof, okay, is a satellite dish, but it is, I think, in one direction only lah. Not too sure about that. So the area in the dish will allow stronger wave to be transmitted, okay, and security is achieved by encryption. The problem here is just the attenuation and diffraction of radio wave. Radio wave very 麻烦 one. You send here, send there, all not good. So as I mentioned just in the lecture video, if you want to just have a general way of answering questions about benefit, right? If they say, why is it not good? because there's a lot of noise, a lot of attenuation, short range, expensive, not safe. Why is it good? Less noise, less attenuation, very cheap and secure. We want less, cheap and secure. That's why you join MCKL, right? Less, cheap and secure. I'm just kidding. I'm kidding. I want my job. Please don't fire me. Okay. So the next one, we go into a bit about satellite. So the thing about satellite is you have to know how to write out the explanation and in this cute little card. Okay. So here you have the dish. The dish will send a carrier wave up. So this is an uplink. Send to this one and then send to downlink. So the transmitter send the wave to the satellite. Satellite will receive a very attenuated wave because by the time the signal reaches the far away satellite, the signal intensity also very small already. So it needs to amplify the signal. Make the signal bigger and send back to ground. Then you receive lor. So let's say this is me, I'm in KL, and this is you in your house across the ocean on top of the mountain, I don't know where lah. Satellite can overcome this. So we don't have to set up many towers in between my house and your house. And we use different frequency because we want to prevent swamping. Swamping is just a different way to talk about interference between the uplink and the downlink. Okay, people have some meeting, some important people have some important meeting and have decided that these are the sets of frequency that you can use if you have a satellite dish that is made for communication. Other frequencies will be used for military. And if you tap them, I think some laws will be broken. I'm not sure. But we don't want CIA to come knocking on your door, right? So we also then compare. These are all the facts they will ask like, oh, the different types of satellite. There's geostationary and polar. So when we saw geostationary satellites, right, this is the main ones that we use because it always appear above the same point. So that's why it is 24 hours. It orbits from west to east and it's very far away. Compared to the polar one, which you can remote control, meaning the satellite can be anywhere. Okay, it passes over this orbit here. Okay, so it is about 100 minutes because it doesn't always have to be on the same spot. Okay, and it can travel over every region on the Earth multiple times. And the radius is small. Okay, much bigger, smaller. Advantages for this one, if let's say your Astro dish, right, once you install the Astro dish on your TV, on your roof, the dish, you don't touch it anymore unless a monkey come and push the dish lah. So because you don't touch it anymore, the aerial can be fixed in position and you don't have to track the satellite because you always know where the satellite is. Geostationary. Okay. And this one can be permanently linked to ground station. So this one is okay. No need long distance cable, low maintenance. This one high maintenance. We need to track because we don't know where the satellite is with respect to the dish. Information signal need to be stored in the satellite before they see the dish again. So this is more expensive because the satellite and the dish are not always talking to each other. This one, the dish and the satellite is always on the same spot. So they will always talk to each other. It's pretty good. But the problem with this is that we cannot communicate with the poles. That's why when you go to the poles, they always have this satellite phone because the phone is linked to a polar satellite. Okay, and the orbit is very large, so there's signal attenuation, there's time delay. If you ever try to have a conversation with a friend over Zoom, you already know that there's a time delay when you talk to the person. Okay, so the solution is to use it together with optic fiber, and this is also quite expensive to launch. Okay, disadvantages is very great resolution because it's close to the Earth's surface. We use it for spying. And there's less lag because it's closer. So if you remember that this one has small radius, all these advantages and disadvantages should come naturally. So this is the first part. A lot of facts about the types of ways the communication signal can go from point A to point B and what are the things that will affect them. There are some either small details that I didn't mention, but it should be enough to answer most of the past year questions. Okay, so communication channel is the first type. You need to know the types and you need to know a bit of detail about them. The next part, in order to answer questions in this section, would be to look at attenuation. So attenuation is not the first time you've seen this. You've seen this for X-ray, you've seen this for ultrasound. But the idea of attenuation here is that now instead of just taking I is I naught E negative mu X, okay? We don't care already. We just want I over I naught or I naught over I, okay? So attenuation in decibel here would be 10 log I1 over I2. So it's just taking 10 log the signal, either noise, signal to noise ratio or noise to signal ratio, it doesn't matter. So if you've watched the video, you will notice that we use MCKL as an example of signal attenuation because we all know MCKL got Wi-Fi. Ta-da! The further away you are from, so these are all the Wi-Fi spots lah. So this part here don't have signal because the further you go, okay, the smaller, the bigger the negative number this one is, so the greater the drop. Last time they only have one Wi-Fi router here. Now they install all these extra Wi-Fi router. Hopefully college got good Wi-Fi now. I don't know. Maybe. Okay. So we use decibel as a ratio. But what you really need to know, right, is just this part. Okay. So I'm just going to crop this whole thing in. Okay. So you need to know how to find bell, which is log 10, the ratio of power or intensity. You can talk about attenuation, which is log 10, P2 to P1, or signal to noise ratio, which is also log 10. And why do we use 10 log 10? It's because it provides a smaller number that is good for ratio. If not, this one will be some weird prefix, and nobody likes prefix, right? And then the gain for the amplifier in series can be found by adding the log rather than multiplication. So when we say adding the log means, if you look at this one, if I go from here to here, the change is just addition because this is multiplication. So I can just add. We'll do a question now regarding this signal to noise ratio. So to be able to do this, you need to try questions. All right. So we have recorded a fair bit of examples. You can go and try. This one all recorded already. I'll just copy here. So examples recorded this. And the signal attenuation equation. Okay, right. This one also quite easy one. My students always say I say everything is easy, but it's true. If you got prepare sufficiently, then it's easy lor. You don't prepare, then everything hard lor. Okay, so we're going to do some questions. I am not going to do the ones that are here. So these are all recorded already. If you need help, you can go and watch in the playlist or the stream channel or wherever it is that you access the videos from. Okay, I'm going to go and dig up some more recent questions. Okay, so this didn't come out in ON20. I'm not saying it will come out in May, June 21. I'm just saying it did not come out. Okay, and very weird one, there's no communication in variant 4.1, which is anomalous. Most of the time we will expect one question. Okay, so let's dig up something more recent to try about attenuation. Okay, and do May, June 19 paper 4.2 an example. Okay, so here as usual, you are asked to state what is meant by attenuation and noise. I've mentioned just now in the notes already. Wait, a bit blur. Let me crop. Then the recording lagi cannot see. Okay, there we go. Attenuation and noise. So attenuation here is the decrease in signal power. as it travels along the transmission line, if you don't want to talk about medium. Okay, the decrease in signal power as it travels across the transmission line, since we are talking about signal transmitted there. Okay, noise. Noise is unwanted signals. So unwanted random signals that superimpose with the information signal. Signals that we don't want. Okay. The initial section of the transmission line for a signal of a telephone exchange is illustrated in figure 5.1. Beautiful. Show you what that looks like. Okay. So as the exchange, the input signal to the transmission line has a power of 2.5 times 10 power negative 3 watt. So the input here, P in, the energy here, actually it's here, P in. So this P in is 2.5 times 10 to the power negative 3 watt. After the signal travels 52 km along the transmission line, the power of the signal is 7.8 times 10 to the power negative 6 watt. So it is significantly attenuated. So here, the signal, let's say this is PS, is 7.8 times 10 to the power negative 6 watt. Calculate the attenuation per unit length in decibel per km in the transmission line. So we want attenuation, right? So we will take 10 log the ratio of the input to output, or in this case, I will take PS over P in. Okay, this will be equal to 10 log bracket 7.8 times 10 to the power of negative 6 divided by 2.5 times 10 to the power of negative 3. Okay, a note about your calculator and you. Let me change back to computation mode. When we press calculator for this one, can you please make sure that you know what you're pressing? So if you cannot, or if you're not familiar with the brackets, it's okay to do step by step like this. 10 log answer. So 10 log not lon. Don't press the wrong button. Log the answer. Close the bracket. Okay, negative 25 decibel. So hence, attenuation per unit length will be negative 25. What is the length? 52. Divided by 52 km. So that would give me 25 divided by 52, 0.48. 0.48 decibel per km. Okay, you can leave the negative here. It doesn't matter. But the negative sign is actually to show that the power decreases along the line. But if you decide to just keep the positive number, it's okay. All right, next. The gain of the amplifier is 115 decibel. Calculate the power of the signal at the output amplifier. So this is the gain, meaning now we will increase the intensity of your signal. So at the amplifier, right, this one is PS. Your signal was 7.8 times 10 to the power of 6. Right, still ratio. 7.8 times 10 to the power of negative 6 watt PS. And then this out here, whatever the amplifier does, we want to find the output signal. Let's say I call this P out. The gain here is 115 decibel. So what I could do, is I will do something like 115 positive is equal to 10 log. If it's positive, I'll take the big number, amplified already. Of course, the output is bigger. Divide by the small number, 7.8 times 10 to the power negative 6. So all this decibel thing is just ratio of power, add a log 10 log 10 in front. 10 log 10. Positive. Press calculator. Okay, how to press this one? I'm based on the over and divide. Okay, so this is 11.5 is log out over 7.8 times 10 to the power negative 6. Normally I leave it like that, but I notice some people may need a bit of help. So you see this log, how do you press log? Okay, I cancel everything first. When we have log, right, whenever we want to reverse the mathematic process, we can always press shift. For example, if you press shift, this is all the, I know you cannot really see, but it's all the brown buttons here. So this will be 10, because you bring over here 10. So it's 10 to the power of 11.5. Okay, so most of the time I don't write this, but for the benefit of discussion, I will now. 3.16 times 10 to the power of 11. This will be equal to P out over 7.8 times 10 to the power of 6. You see its answer? Then we multiply 7.8 times 10 to the power of 6. So your output, 10 to the power negative 6, my bad. So if this happens to you, you can always go back, press equal again, and then go back. Change this is negative 6. Ta-da! Is it correct? Hang on, just to make sure. 10 to the power of 11.5. This is a very large signal power. Ding, ding. 115 decibel. Okay, sure. So 10 to the power 11.5 multiplied by, this is negative 6. So answer multiplied by 7.8 times 10 to the power negative 6. I'm feeling a bit paranoid, so I'm going to include a bracket. Okay, so it feels legit. 2.46, 1, 2, oops, it's gone. 2.46. Why you crash? Why? Hang on. At least my physical calculator won't crash. 1, 2, 3, 4, 5, 6 times 10 to the power of 6. This is your output signal. I guess we need a lot of power for this one. $115. Did I press my calculator wrongly? 2.5, 7.8, Nani? Dun, 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 dun. 2.4. Wait, let me double check. Something feels very weird because this is very big. Negative 3, 52 km, 115, negative 6. Attenuation per unit length. You see this? Here's the mistake. Wow, no one say anything. Purposely, is it? So there's a 1 here. Sorry lah. If it's too small, the prefix is too small. Miss Lee's old eyes cannot see. So there's time to press again. So 10 log 7.8. Why you no say anything, people? Negative 16 divided by 2.5. Wait, unless you say something and I don't see notification. Nope. No one said anything. It's okay. It's just me then. Wait, where's my exponent? Dun, -3. Is it correct? -125. Okay, so I'm gonna add a 1 here and add a 1 here. So 125 divided by 52 would be, yeah, I didn't see, you also didn't see though. I should go and refill my coffee. It's okay, it's fine. 52. 2.4. Okay, boss. This is 2.4. Which means this one, there's a 16 here. Ayo, one prefix, the whole question can crash to the ground. Which is why normally when I do prefix, I make sure I write carefully. But do too many questions already since Wednesday. My brain is a bit jelly. Because I'm also doing AS. So AS A2, AS A2, my brain is a bit. Pew. All right. This one's all okay. We can still keep. Actually, this one you just change the power, can you? 11 plus 16. No, 11 minus 16. So this one will be -4. Because 3 times 7 is already 21. So -5 become -4. Okay. So this is how I know that the answer is a bit out. Prefix is too big. Okay. That's why I was hesitant in the beginning. And this could also happen to any one of us during the exam. So if your answer is too big, especially this kind of attenuation one, you're like, oh no, something is wrong. Maybe I copied the prefix wrongly because that happened to my teacher. Yeah. Hopefully it won't happen to you lah. You have bright young eyes. I don't. Okay. So the input is here. You can see everywhere. I don't know why I missed out the 16. So if we put in the 16, then everything makes sense now. So this calculation is worth 5 marks in total. This is 2. So if we see 10, this substitution, you get 1 mark. So you can see if I substitute wrongly, I will get 0. The output is A1. So 0 substitution means, wrong substitution means 0 mark. Very tragic one. So, and if this part, I didn't correct the prefix, then I will only be able to get this C1 mark. Because the answer here is 1 mark. And if you take this ratio and then you divide by 52 is another C1. This 2 is the same C1. This one and this one. Quite dangerous if I didn't double check the prefix. Because CIE's intention here is that you understand, hey, you know, this answer just now, 10 to the power of 6, it doesn't make sense. It's too big now, the power. So if you do enough question, you will be able to get a sense of the magnitude of each one. All right, let's do another one to get rid of the uncertainties in your brain. Let's see. Ding, ding. $17.10. There's a lot of ADC and DAC conversion in the recent days. Not sure why though. Maybe it's their favorite. Let's see. Paper 4.2. Okay, we can do this one. Last one. May, June 15. 4.1. Question 12. I shall crop the question. So, and the last part is a calculation one. So normally when they ask communication channels, sometimes they do ask just explain or write facts, but normally they'll ask with calculation. So here it says that information can be carried by means of various channels of communication. Name examples, one in each case, of devices where information is carried to the device using a wire pair, a coaxial cable, and microwave. Okay. So this one is fax law. So wire pair. Remember I said telephone? Your 3.5 mm jack, so loudspeaker. You know what's a 3.5 mm jack, right? The one that you would have if, let's say, you're wearing a headset like mine. This thing. Okay, so the one that you plug into your laptop. Loudspeaker. We also use this for doorbell. Also use this for telephone. Hello, hello, the Lady Gaga one. Okay. Coaxial cable. Coaxial cable is normally used for TV set. Your audio amplifier. If you play the electric guitar or your electric bass, they have a thicker cable. Okay, microwave is normally used for satellite dish or your mobile phone. Okay, you just know one or two each is enough already. Advantages of optic fiber. Okay, more secure. Always got mark one. The more advanced wires is more secure. Less attenuation. Okay, lor, 搞掂. Finish. What else can you write? Less noise, greater bandwidth. Can stream Netflix. Can watch football live when football was still a thing before COVID. Okay, next. An optic fiber has a length of 62 km with an attenuation per unit length of 0.21 decibel per km. Okay, so I'm going to draw the cable. This mark cable. My cable is too small. This is my Galaxy cable. Okay. The length is 62 km. And the attenuation per unit length is this one. Input power to the fiber is P. So we're going in with P. Noise power is this one. So this is noise. I'll call this PN. Signal to noise ratio is 25 dB. So we call this S and R. Signal to noise ratio. Okay, calculate the ratio in decibel of the input power to the noise power at the receiver. So what we want here is P in over P noise. Do we have input? We have noise power. Okay. We have signal to noise at the receiver. Okay, so one by one, I draw first. This P is your input. So this one is the P. This is the P. Okay, and then there's noise here. So there's P over Pn here. This is my Pn. And then there's also at the receiver. So whatever that comes out of the receiver, I'm going to change color. Let's say I call this P2, P out. Yeah, P2 lah, over noise. So I know the signal to noise ratio here. I want to find the signal to noise ratio here. But I know the attenuation per unit length is 0.21 decibel per km. So I can find the total drop or the total attenuation. So I would say along the 62 km cable, the signal attenuation is equal to 62 times 0.21. What is 62 times 0.21? This is 13 decibel. So that means whatever sound that is here, by the time you reach here, we will minus 13 decibel. Okay. We know the signal to noise ratio here. This one is 25. Something minus 13 is 25. So hence, the signal P to noise at input power at the receiver, signal to noise ratio at the receiver, P to the noise power. Okay, so signal P, this is input. Input to noise is equal to 10 log this one over this one. But also, I know that this point here to this point, we minus 13 decibel. Here is 25. So 38 minus 13 is 25. This 25 decibel is P2 over Pn. I mean, it's 10 log P2 over Pn. So this 38 is another 10 log P over Pn. So this one is actually equal to 25 plus 13 plus this 13. So you will get 38. Okay. So this is why we look for the attenuation per unit length. And this is what we mean by when we start this process, why do we use log? Because the gain of the amplifier is found by addition. So right now the gain is negative 13. So I just need to add negative 13. So 38 plus negative 13 will give me 25. Okay. So if you want to know a bit detail about how the log can be put to addition, you can watch the videos because we explained that. It will take another 20 minutes lah. So in the interest of time, I will not do that. So the whole idea here is that we can ratio many things. We can ratio P to Pn, P to Pn. If we are ratioing the same thing, which is the noise power to the signal power. So here we want, see, input to noise. And what is given is signal to noise at the receiver. Here. So they are both to noise, And because they are both to noise, if you think about ratio, right? Oh, it's not here. If you think about ratio, they will cancel out. A plus B. Let me show you. Give me a sec. Signal to noise. Like this. In your notes. Okay. So one is this part here over noise. This one here over noise. You flip it, lor. When you flip it, the noise and noise can cancel out. So I can just add. But when I add and flip, it becomes minus. Okay, so go and look up at the explanation for this here in the videos if you need it. Okay, if not, you can just take it at face value lah. All these 25 is just ratio. If you want another ratio, I can add how much the signal power drop. And now using your answer in 1, determine the input power. So 10 log input power over noise is equal to 38. So I can take log input power over noise 9.2 micro negative 6 is equal to 3.8. Okay, this one we have more manageable powers. So I'm not going to show our press calculator again. So I'll just quickly dial in the numbers. 10 to the power of 3.8 times 9.2 micro. That would give me 0.058 watt. Makes sense. Again, the powers should be very small. Cannot be very big. Okay. And it's 2 marks, so they don't expect you to do a long-winded calculation. Because if you check the notes, or the example recording, give me a sec to find it. Now, so I got explained part by part how they cancel, what to do, and why you can just add. But if you don't want to think so much, you just add lah. When the signal travel, it will attenuate. Oops, cannot pen. Okay, so this one you do long way. This one is a shorter way. If you already know this, you can bypass this one. Okay, so if you need a bit more explanation, you can go and watch the recording of May-June 17 paper 41. This is May-June 15 paper 41. Okay, so other questions that you can try if you need some recommends to do would be, I mean, I know we recorded quite a lot, but you could try, just try some lah. You don't have to try all. So that will be signal attenuation. Try. All these need to calculate one. So if you don't try, then it will look very intimidating. You can do this. Maybe choose half from this list. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Choose a few lah. Only just choose 5. Any 5 lah, doesn't matter. Just choose any 5 to do so that you know how to use the ratio. Okay? It's not all okay. There are so many. I just choose a few only. Okay. If you want the entire list, it's in your OneNote. Okay, what else are we missing? Let's go back to the block diagram. So we have done the communication channel and attenuation. We have done the receiver. We have done everything except the actual signal itself, which is AM and FM modulation. So the third part, when we talk about AM and FM modulation, it is less popular because these things are quite outdated lah, and communication will no longer be in the syllabus starting 2022. Everything is outdated already. We don't really talk like this anymore. Do you still listen to a radio? You still tune a radio? Turn on your radio, pull out the antenna like the olden day TV, and then just listen to a static? No lah. Who does that anymore? I don't. Do you? Okay. So when it comes to AM and FM, what we need from you is basically compare them. Okay. So compare AM and FM. I'm just going to give you a slightly different note for variety's sake, but they are also completely in the notes lah. Okay, so this is the advantages and disadvantages. But if you want to think about a amplitude modulation is when the amplitude changes together with the carrier wave changes together with the information signal. So something that looks like this. So when this signal is maximum, This one not very aligned also. I don't like this. It's not a good graph. BRB. I have better graphs. Okay. Okay, your notes lah. The graph here is better. That one from the book is not so good, not accurate. So whenever there's large amplitude, here is large amplitude. Negative amplitude, small amplitude. Frequency modulation when there's large displacement, large frequency. Low displacement, low frequency. You need to know the definition. Which one is constant? Which one vary in synchrony with the displacement? So AM, amplitude changes in synchrony. FM, frequency changes in synchrony. You also need to know the bandwidth for AM and FM. This one I think is relatively straightforward. So you should go and watch the video about AM and FM. What is bandwidth? But just a very quick one. Bandwidth is the range of frequency occupied by the AM wave. So what kind of frequency is acceptable? Okay. So the way we calculate bandwidth, again, this is just I tell, but the derivation is too complicated. All right. So let's say this is the carrier wave frequency. To find the bandwidth, we will plus or minus the signal frequency. Okay, so this carrier wave will have its own frequency, high frequency. The signal, which is the voice or the music, will have a lower frequency. To find the bandwidth, it is this frequency plus this frequency and this frequency minus this frequency. Plus minus. That's all. AM, not so good because no quality. Good because travel far and cheap. FM, good quality but more expensive. That's the general idea of AM and FM. Nothing much now. Okay, so questions are like this lah. Okay, they will ask you to define AM and then ask you why we modulate. We modulate so that there's less interference, so we can have more radio station operating in an area. So the modulation becomes a signature. Like for example, when you look for your friend, your memory is modulated to the presence of your friend. You know how your friend looks like. So you ignore all the other faces. Modulation. No? So it's a signature. When you tell your radio to only tune in to 92.9 hits.fm, your radio is going to ignore all the other signals because FM is modulation. We can use a shorter area, especially if the carrier frequency is high because the wavelength is short. There's less distortion, there's an increased range. So whenever you don't know why we do this, you just say increased range, less attenuation, less noise, maybe you can get Mark 1. Okay. All right, so here, you can see that there's a bandwidth situation happening here. So if you're asked to find the wavelength of the carrier wave, we can use V equal to F lambda. So all these wave is still radio wave, so we can put in the speed of light. And we know the carrier wave frequency is 909. So we put inside and then we can find, wow, this wavelength is so long. Yes, radio wave ma. Okay, and then you are asked to find the bandwidth. Bandwidth here is just the width of the band, this one. So it's 900 to 18, so 918. So it's 18 hertz. Okay, and the maximum frequency of the transmitted audio signal is 9 kilohertz or 9,000. So let me zoom out a bit. Okay. So for this one, if you want to find the maximum frequency that we can go, we are looking at the bandwidth divided by 2 because we can go all the way from 900 to 918. So minus low. Okay, and then when we divide by 2, there will be 9 kilohertz, just one side band. The side band would be the maximum frequency. Okay, so all these, right, there are a lot of detail that they just don't include in the syllabus, but they expect you to answer this kind of level 1 question. So right now it's just memorizing the facts, lor. Sorry. Because I'm also not a communication engineer, and I also don't know why they build it this way. All right, so you can take 918 minus this one, or you can take bandwidth divided by 2. Why is the maximum frequency not 918? Because this is the signal, right there. The signal, not the carrier wave. So we only look at the signal. So if you think about your transmission, right? Why don't we take the carrier wave is because we are marrying this signal, which is the sound, to this carrier wave. We don't really care about the carrier wave frequency. We care about this signal frequency. So in AM modulation, if I say something along the lines that if let's say this voice or this music or this information signal, it changes too much or too quickly, then this AM signal cannot change fast enough. So the carrier signal have to be a certain, this signal, information signal, have to be at most 9,000 hertz. So it's not the carrier signal that carries the information. It is the information signal that carries the information. The carrier signal is just like a background signal. So we use this to disturb this to get this. So this one doesn't carry your information. See the name? It's information. Information carried by the carrier signal. So if you go back to the question here, we want to know how much information can be carried. So the maximum information that we can carry is 909 to 918. So it's either plus minus your information signal. So basically they're asking you what is FS lah. You look at this one, FS will be 9 lor. Because this one is carrier plus signal. This one is carrier minus signal. So they're asking us, what is the signal frequency? Transmitted signal. Does that answer your question from the chat? So the information signal or the audio signal is the one that tells you how much information you can send. The carrier wave is just like background. Use this to disturb the other one. Okay or not? As I wait for you, I go and dig out another question. Wait, Fishbone. M19. Yes. Okay, we'll do one last one. So this is AM modulation. And then we're going to talk about FM modulation. I will just mention that you should review May-June 13 paper 41. This is also recorded lah. Okay, so know the difference between information signal, which is where the data is, versus carrier wave signal, which is not where the data is. All right, we're going to look at this question that is not in the handout. This is from Winter 19. ON19, paper 42. Question 6. I like to call this the fishbone question. It reminds me of a fish. And you can see this variant, the communication question is only 4 marks. A bit sad, but it's okay. So this is, this is not FM, this is AM modulation. So you can see the amplitude decreases. The sinusoidal information signal has a frequency of 10 kilohertz. Okay, so this is FS. Let me change pen. This is FS. Miss, what is FC? You want to find FC, can. In fact, they ask you to find the frequency of the carrier wave, FC. They're not the same thing. So this is the, okay, let me show you. Let me explain now. You see this envelope here? This one is probably going to go up again, right? I mean, if it's assuming it's sinusoidal lah. So here, all the way to here is the signal period that we seldom call period. We will ask you to find frequency one. Okay, so if you want to find FC for this case, you will have to take here to here, which is 5, or maybe if you want to just be extra sure, here to here is 10. So this is the carrier frequency or period from here to here. 2T. So they're not the same thing, because this carrier wave cannot respond if, let's say, this signal is too quick. The signal frequency is too large. So anyway, we want to find the carrier wave frequency. We can find the period. So I'll just put period T will be equal to 5, or 2T is 10 microsecond. So times 10 to the power negative 6. So T will be equal to 5 times 10 to the power negative 6. This means FC will be equal to 1 over 5 times 10 to the power negative 6. 1 over 5 E6. This will be 20,000. Or 1, 2, 3, 4, 5. 2.0 times 10 to the power of 5 hertz. I prefer to write it in kilohertz because the signal is already in kilohertz, but we shall see. On figure 6.2, sketch the frequency spectrum, which is the bandwidth spectrum, of the modulated wave. So this carrier wave FC is 2.0 times 10 to the power of 5, which is also equal to 200 kilohertz. Correct? 200 ma? Yep. The signal frequency is 10 kilohertz. So Fs is 10 kilohertz. So we are drawing, I didn't include, we are drawing this one. You see, frequency here, amplitude here. Frequency here, amplitude is related to intensity, so it works too. So does it matter where you draw? Well, I will draw in the middle. Of course, they tend to draw in the middle. So this is 5 boxes. I will draw here. Wait, 1, 2, 3, 4, 5. So I'm going to draw one here. So this line will be the carrier wave frequency. And I'll label this one as 200. This is already kilohertz. Then plus minus 10. Means need to start from 0. Yeah, they start from 0 already. But then they start horizontally from 0. Let me check the mark scheme. I don't think you need to. But let me check. Winter 19. Winter 19. Paper 4-2. This is question 4. Six actually. Okay, so it doesn't matter as long as you label the value. Okay, so that means I can draw anywhere I want now. I'm just going to draw here, okay. One here, and then maybe one here. As long as they're equally spaced, because this one will be 210, this one will be 190. Okay, that's all. 3 marks. I show you the mark scheme. 3 line, get 3 mark. Very nice. 3 equally spaced vertical lines. Okay, they look equal to me. 2 outer lines are equal length. Center line is longer. Okay. 3 vertical lines and no more lines shown at 190, 200, and 210. So you don't really have to start from 0. You can start from anywhere. How close, how far doesn't matter. Okay. So this one is AM modulation. It's easy. That's why it's seldom asked lah. Because I think they kind of expect that. And also the modulation thing is a touch bit outdated. All right, we're going to move on to frequency modulation just pretty quickly. So to see FM modulation is this one from ON15 Paper 41. You can go and watch the video. They will just ask you what is the signal, what is the minimum and maximum frequency, because you are going to squish the wave. Remember? You're going to squish the wave like this. So what is the maximum frequency and what's the minimum frequency here? Go and watch. So I would suggest to watch these 2 examples, AM and FM. And there are not many questions to try. So I'll pick 2 for you lah. These are all the questions in past year that have been asked so far. Okay, so maybe you don't have to spend too much time here. These 2 we discussed already, so you just pick 2 and 3 to do. Any 2, any 3. I've also discussed this one already. All right, so go try out the questions. That's it for communication. So we go back to the block. Main question here is ADC to DAC transmission. Okay, go try some questions regarding this. The attenuation situation and the communication channel. Try some examples according to this. So maybe you do 4 questions here, 4 questions here. And then after that, the AM and FM, which is also this part, because when you send out the information, because this is the information. The so-called information signal is this ones and zeros. This is your information signal. We do digital modulation now, but digital modulation is not your syllabus now. So this can be considered your AM and FM. Okay, it's a bit like using a wooden stove to boil your water. You can, but we have more modern ways to boil water. Just like we have more modern ways to send out information signal beyond AM and FM. This one is very old technology. All right, so you should know a little bit, but it's like the basic. So just do maybe 2 or 3 questions here. Then that would cover at least 6 to 10 marks. Can I? Unless they decide to just throw you and don't ask anything, which happened, I think, once or twice. Then the students are devastated, but your luck low. Okay, so that is communication. I will stop the recording now, and I'll see you in the next recording.